Section 11.5, lines and planes in space. So let's start with this section. We're going to start line, then we're going to do the planes. So line, how is it like the line? So look to this example. Here's the line with 2 points, P, X1, Y1, Z1, and Q, X, Y, Z. So always, when you hear line and they're going to give you only 1 point, how are you going to choose another point? You have to choose any random point and plug in the point in the equations of the line. So if it's satisfied, that means you're going to get 2 points belong to this line. For all the examples you're going to get, they're going to give you only 1 point. If they ask you to find the distance, if they ask you to graph it, they're going to give you only 1 point. How to find the other point? You can check that when we do an example. So here's a line. So line PQ. And if you see here, they give you only the point X, Y, Z. Then they're going to choose another point X1, Y1, Z1. That means the line is going to be PQ. And here's the vector. If you look to the vector, it's exactly the same direction with the line. This is a direction vector. Direction vector to the line L, which is the line L, PQ. Here's the direction vector ABC. So let's put these together. If this one parallel to the line, that's mean if you look here, remember two vectors with the same direction. That's mean if this is L and this is V. So there is a scalar. If you multiply by L, it's going to be the vector V. But in this case, the line is longer than the vector V. That means there is a scalar. Here's the line L equal the scalar T times the vector V. A line is parallel to scalar times the vector V because they are the same direction. That's what we're going to check on the next page. So they're telling you PQ, which is the line, equal the scalar times the vector V. Now let's just extend that. PQ are 2 points. P is X1, Y1, Z1, and the Q is the point X, Y, Z. So PQ, that's the X minus X1, Y minus Y1, Z minus Z1, which is the line, equal the vector V, which is A, B, C times T. So this is exactly the same thing. PQ equal T times V. Let's extend that. That's mean X minus X1 equal 80. X minus X1 equal 80. Y minus Y1 equal BT. Z minus Z1 equal CT. Extend this variable by leaving the X here and move the X1 to the other side and move the Y to the other side, Y1, and move the Z to the other side. These 3 equations for parametric equations. So when they ask you, find the parametric equations, you have to get a point and a scalar and a vector. Sometimes there is no scalar, but there's a vector. You have to write down point Q and the vector V. This is important to write down any parametric equations. So if you look to the next page, parametric equations of the line in space. Let L parallel to the V, vector V, which is here is the component of vector V, and passing it through the point, the line passing through this point. So the parametric equation is going to be X equal X1 plus AT, Y equal Y1 plus PT, and Z equals Z1 plus CT. There's another type of equations called symmetric equations of the line, which is X minus X1 over A That means t, if you solve this one for t, you're gonna move x to the other side, so it's gonna be x minus x1 equal at. That means divide both sides by a, so t is going to be equal x minus x1 over a. The same thing here is going to be t equal y minus y1 over b. On this one, c is going to be c minus z1 over c. So this is t. T, all t equal, that means this one is going to be equal to this part, equal to this part. That's why we got the symmetric equations. So now I just needed to know theorem, parametric equations, and the symmetric equations. There's an example. So you look to this example, find parametric and symmetric equations of the line L that pass through this point and parallel to the vector V. So we have a point, we have the vector. So you see x is going to be x1. So here's the point 1, -2, and 4. That means this is x1, y1, and z1. So x is going to be x1 plus a, because here's the vector, so this is a, b, and c. X equal x1 plus a, t. This is the first one. The second one, y equal y1, which is -2, plus b, it's 4t. And z equals z1, which is 4 minus y, because here's the c, minus 4t. So this is, we have here the 3 parametric equations. Here's the symmetric, x minus x1 over a, y minus y1, because it's 2, -2, so it's going to be +2 over b, and z minus z1, which is 4 over -4. This one, if you write down this, is going to be right. If you write down like this, just flip in these, it's going to be 4 minus z over 4, so also is going to be right. This is just a simple questions, for example, about how to write down the parametric equations. Let's keep going. The second part, the planes in space. And instead of line, now we're gonna get a plane. So check, here's the plane. And the same thing, P is a point on the plane. Then having a non-zero normal vector. So here's the point P on the plane, and having a non-zero vector n. So here's the non-zero vector n as shown in the graph. The plane consists of all points. Now, all points here on this plane with the point P. So you see, now we're going to choose a random point, Q, which is a point also on the plane, for which the vector PQ, now here's the point P, and here's the vector Q on the plane. The vector PQ, it's a new vector, is always going to be orthogonal on this vector. This is really important because n is a normal vector, always going to be orthogonal to the plane. So if you choose any vector with the plane, that means the normal vector is going to be orthogonal on this new vector. That means here's the normal vector, and here's the new vector. The dot product between normal vector and the new vector is going to be 0 because they are orthogonal. Here's the n vector, which is the ABC, and here's the new vector PQ, x minus x1, y minus y1, z minus z1. Then we're gonna do the dot product. A times this one, plus B times this one, plus C times this one. This is the standard form. And we got a new form. It's called the standard form of the plane. They ask you find the standard form. You have to get a normal vector and a new vector. In this case, they're going to give you only a vector n and 1 point. So to get a new point for the plane, you have to plug in random number on the equations of the plane to get the new vector. So now this is the we're going to do examples also on OP side, how to find the standard form. And also there is another definition you can see next page. The standard form of the plane in space is going to be, they're going to give you a point, having a normal vector. So it's going to be ax minus x1, by minus b1, plus z minus z1. Z minus z1 equals 0. Now, here on this case, x1 is a number. So this is a number. Y1 is a number, Z1 is a number. So if we simplify this one, that means we're going to distribute A, B, C also numbers. So from here is going to be AX minus AX1 plus BY minus BY1 plus CZ minus CZ1. I'm just working on this side. If you check this one, multiplication of two numbers, multiplication of two numbers, multiplication of two numbers. That means you can combine these three together as one number, which is I'm going to write down here as a D. So this one is going to be D. These three numbers is going to be a D. So the left is going to be AX plus BY plus CZ plus D, which is a number because we can combine these three numbers to a D equals 0. This is called the general form of equation of the plane. So here is the general form. That means we have a standard form and general form. If you look at this example, they ask you find a general equation of the plane containing these points, 3 points. So we have only 3 points and there is no normal vector. We have to find a normal vector that's orthogonal to the plane. How are we going to find that? Check this one. There's a theorem, you have to check that. Check the steps. So when you grab these 3 points, here's the location of these 3 points. The first thing, we're going to create a vector between any 2 points. It doesn't matter. So choose these 2 points to create a vector V, and choose these 3 points to get another vector U. How? Here's the vector. U is going to be, that means you're going to choose this one and this one to create a vector U. So it's going to be 1 minus 2, 4 minus 1, and 1 minus 1. Here is the first vector, U. The second vector is going to be on the plane. It's going to be vector V, which is the point, these 2 points. So it's going to be -2 minus 2, 0 minus 1, 4 minus 1. You have to choose any 2 points to create 2 vectors. And here's the thing. I have 2 vectors. How are we going to create a normal vector? There's a theorem, if you check the previous section, the cross product between these 2 vectors equal the normal vector. Why? Because it's going to be orthogonal on the plane. So we're gonna, if you use the cross product between U and V, you're gonna get a new vector, and 100% the new vector is going to be orthogonal on the plane and orthogonal on any points on the plane. So here's the cross product. We got a new vector 9, 3, 13. This is the normal vector. Now, I need to find the general equations of the plane. I'm going to choose the normal vector and any points to the plane. That's when if you go back here, here's the plane. I have 2 vectors here. I found a new vector. Check. Here's the plane. This is the whole thing is a plane, 3 points. I found a vector that's orthogonal on this plane. 100%, this is the normal vector, because the cross product between u and v, here's the cross product. The cross product on nu and v is a new vector, is always orthogonal on the plane. That means here's the normal vector, which is always orthogonal on only points here. Orthogonal here, orthogonal here, or here. Then I'm going to choose this normal vector and any point to find the general equations of the plane. So here's, I choose this point, 2, 1, 1, and I have the normal vector 9, 3, 13. So A, x minus x1, by minus b1, cz minus z1 equals 0. A is going to be 9, x minus 2, b is going to be 3, y minus 1, and here's c. This is the standard form. Simplify this one by distributing 9 and 3 and 13. Combine the like terms, 9x, 3y, 13z, 18, negative 18 minus 3 minus 13 is going to be negative 34. This is the general form. So this example is really important because we're going back and use the cross product. And there's another one is going to be on website. So cosine theta is going to be the dot product between normal vector from the first plane and the normal vector from the second plane, the absolute value over the length of the first normal vector times the length of the second normal vector. These two notes here are important because two planes are perpendicular if the dot product equals 0, parallel if there is a scalar multiple between these two normal vectors. So instead of checking these two planes are orthogonal, perpendicular, or parallel, just get the normal vector from the first plane, normal vector from second plane. If the dot product equals 0, it's going to be orthogonal or perpendicular. If it's scalar multiple, so it's going to be parallel. These two notes are really important because we're going to use it when we're doing the example.
No.
Let's keep going. This is important. How to sketching planes in space. They're gonna explain everything with the example, and always you're gonna do this one on this. If they ask you to sketch, and we're gonna use the same steps on the next section. But the next section is going to be easier because when you do the examples on design, everything is going to be just multiple choice. Let's check the example. They ask you, consider the plane, you see X, Y, Z. That means we're gonna sketch a plane in 3D with X, Y, Z. So how are we gonna sketch this one? We're gonna divide the plane in 3 traces. The first trace is going to be the XY, because you see the plane is supposed to be on a 3-dimension X, Y, Z. This is D, let's say this Y, and here's the X. So first of all, we're gonna sketch the plane on the XY. Look, on this side, how's going to be the plane? Then we're gonna sketch on this side, on XZ trace. Then we're gonna graph it on this side on YZ trace. Then we're gonna put everything together, the points together is going to be the whole graph on XYZ. That means the graph of the plane. Let's check that. You can find XY trace. How we're gonna graph on the XY trace? We're gonna assume that Z is 0. Plug in 0 here. Here is the XY trace. How we're gonna, now I'm just working on XY trace. How we're gonna graph this one? XY trace, how we're gonna graph it? We're gonna let X equals 0 to find the Y. That means I'm gonna plug in X0 here. So it's going to times 0 plus 2y equal 12. This one is 0. That means y is going to be equal 12 divided by 2, 6. That means the point is x is 0, which is the y-intercept with the xy trace. Sorry, the x-intercept. Yes, the y-intercept. So 0, y is going to be 6. And we already assume that z is 0 because we're working on xy trace. So it's going to be 0. This is the first point on xy trace. Then we're going to find the other intercept, the x-intercept, by let y equal 0. So I'm going to let y equal 0. That means it's going to be 3x plus 2 times 0 equal 12. That means x is going to be also equal 4. So x is 4, y is 0, and z is 0. Here's the second point. Now I have 2 points. I can graph this one. It's going to be on the y coordinate. And graph this one is going to be on the x coordinate. That means these 2 points, when you graph it, is going to be for the first trace x, y. Now we're going to do the second trace, x, z. We can do that. Let's do it on paper. So here's the first 2 points, because the second steps they're not going to show you. Now the second trace is going to be, let's say, xy, we got it, xz. For the xz trace, you're going to let y equals 0. That means y equals 0. So the equations is going to be 3x plus 4z equal 12. Now I need to graph this trace, which is the xz trace here. Let's get the point. I'm going to let x equals 0. That means 3 times 0 plus 4z is going to be 12. That means z is going to be equal 3. So the point is going to be x is 0, y it's already 0 because it's xz trace, and z is a 3. On the same trace, I need to find the other point, so I'm going to let z equals 0. That's mean 3x plus 4 times 0 equal 12. That means 3x equal 12, so x is going to be equal 4. So the point here, let's check the point here. X is 4, y is 0, and z is 0. So here's the second point. We're done from this trace. We need to go ahead and work on the third trace, which is x zy trace. On zy trace, you're going to do exactly the same steps. Let's do it. So zy trace. We're going to let x equals 0. So x equals 0, that means I'm just going to write down the equations. X equals 0, so it's going to be 2y plus 4z equal 12. We need to find the point. 2y plus 4z equal 12. I'm going to grab this trace, so that y equals 0, that means 2 times 0 plus 4z equal 12. So z is going to be equal to 3. So the point is going to be x is 0, y 0, and z is a 3. Let z equals 0, that means 2y plus 4 times 0 equal 12. So y is going to be 6. So the point is going to be x is 0, y 6, and z 0. If you check, I got 2 points for this trace, 2 points for the xz trace, and 2 points for the xy trace. Put these points together. Here's the final graph. So this is the graph for the trace. You see these points, 0, 0, 3, Between the YZ trace, we get these 2 points. Between XY trace, we get these 2 points. Between XZ trace, we got these 2 points. Put these points together, this one's going to be the graph for the plane. Okay? So they just give you 2 more notes. If the equation of the plane has missing variable, as you know, the plane in 3D, that's X, Y, Z. But if there is missing variable, then the plane must be parallel to the axis represented by the missing variable. So here you're missing the Y, so the new plane is going to be parallel to the Y coordinate. If you're missing Z, the new graph for the plane is going to be parallel to the Z plane. If you're missing X, it's going to be parallel to the X plane. That means like this, or parallel to the Z plane. This is not just to show you that. And here's another note. If you're missing 2 variables, in this case, it's going to be parallel to the coordinate plane represented by the missing variables. So here, we're missing XY. That means the new plane is going to be parallel to the XY. Parallel to the XY coordinate, that means like this. If you're missing like this one, missing XY, so it's going to be parallel to the XY plane. On this one, we're missing XZ, so it's going to be parallel to the XZ plane. Here, we're missing YZ, so it's going to be parallel to the YZ plane. To find the distance, the next part. To find the distance between planes, point with the planes and a point with the line. There's 2 rules. Check here. We're going to study finding the distance between a point and a plane, and we're going to study finding the distance between a point and the line. So you have to be careful from these. You're working with the plane or you're working with the line. Because if it's a line, it's going to be different rule. If it's a plane, it's going to be different rule. So if you look to this graph, we're going to study the distance between the point P and a point Q. That means, you see P, it's belong to the plane, and Q is a point outside the plane. You need to find the distance between the plane and the Q. What are we going to do? Here's the new vector. They're going to give you the Q. In this example, when they ask you to find the distance, they're going to give you the Q, which is a point outside the plane. You need to find a point on the plane. Then find a vector from this point to this point. We're going to get a new vector. They're going to give you a normal vector. Here's the normal vector. The distance between the plane and the point is going to be the projection of this plane, this line, which is the vector here, we got it, to the normal vector. The projection of this line on the normal vector. This one is going to be the distance between the point Q and the point and on the plane. Let's check that next page. So that's what they're telling you here. The distance between a plane and a point Q, not in the plane, it's outside the plane, is the projection of PQ over N, the normal vector, which is the dot product between PQ and the normal vector on the length of the normal vector, where P is a point in the plane. This is important because they're not going to give you a point in the plane. You have to choose a random point and plug in the equations of the plane. They're going to give you the equations of the plane. So to find the P, plug in any random point on the equations of the plane. If it's satisfied, both sides are equal, that means this point belongs to the plane. So you can use P, the new P with the Q. Normal vector to the plane N is a normal vector. We're gonna check that when we do an example. And the last thing, if you check the next one, there is an example. So you see, always choose like these points. Make one of the coordinates equals 0, negative d over a. This is the easiest one to choose. The point, this is the easiest one to choose, or you're just gonna choose another point by plugging a number in the equations of the plane. Here's an example. Find the distance between the point Q and the plane given by this equation. The Q is outside, and here's the plane. Where's the normal vector? This is the plane. That's mean A, B, C is the normal vector. Here's A, here's B, and here's C. So this is the normal vector to the plane, which is orthogonal to any point to the plane. To find a point, here's a point. How are we going to find this one? It's a random point. So by saying that negative d over a, let's check that. Here is the d. So it'll be negative 6 over negative 6, because this d is going to be here, over a, which is 3, so it's going to be 2. This is the easiest way to choose a random point. Because it says negative 6 over a, you can use this formula to find a point belong to the plane. D, because D is going to be minus 6 equals 0 on the left side. So it's going to be negative 6 over 2, 3, which is the A. So it's going to be equal to, that means I can choose the point 2, 0, 0 as a P belong to the plane, point P. Now, the vector from P to Q is going to be, here's Q, 1 minus 2, 5 minus 0, negative 4 minus 0. Here is the P. So now we have a vector PQ and we have a normal vector. To find the distance, we're just going to use the projection rule. This is going to be the projection, the dot product between PQ times n over the length of n. So here's the dot product. Absolute value always, because the negative is supposed to be positive. There is no distance with the negative. So it's going to be 16 over square root of 14. You can keep it like this, or you can convert it to a small number.
Sir, how did you get the 0.200 again? Like that was kind of confusing.
Yeah, here's a formula. They mentioned that here.
Mm-hmm.
You can use this formula to create or to find a random point. So here, you can choose any point here. Like for example, to choose, you have just make sure choose easier point, okay? So if I said, if I plug in 0 here and 0 here, that means this side is going to be 0. The left here is a 3.
Yeah.
3 times which number is going to be 6? 3 times 2 is going to be 6.
Yeah, so x is equal to 2.
Yeah, that means I can choose x2, y0, and z0. But you can choose this formula. You can use this formula, okay?
Mm-hmm.
So here's the equations: 3x minus y plus 2z minus 6 equals 0. This is the general form, right? The right side equals 0. So this is the d. They're telling me there's a formula. You can choose d and divide it by a to get a point. They say negative d
I get it.
divided by a with the 0, 0. This is a best formula to create a point belong to the plane. Okay, but make sure to move the d to the left side.
Yep.
Because if it's not, it's going to be wrong. Okay.
Okay. Yeah.
The last part, which is here's the last part. This is the same thing. They just make it in details. To find a distance between a point and a line. Now this is different. This is not a plane. So check is going to be the cross product between, again, we have to create a point P and find the vector here, the cross product between PQ and U over the U is also a direction vector. Direction vector with the line. That means it goes with the same line. It's not orthogonal on the line. It's direction vector over the L, where U is a direction vector for the line and P is a point on the line. So this is the difference. You have to be careful. If it's a line, you have to use this form. If it's a plane, you have to use the other form.